All right, everybody. So welcome to the Day 2 for the discussion. I guess before that, uh, I also want to remind you guys that I will always upload my slide onto CCLE, and each day after the discussions ends, I also post the recording over here in the video file. It's going to be MP4 file, but I think that for somehow CCLE doesn't play the file automatically if it's under the folder or something. So I just upload it onto YouTube video, onto YouTube channel too. It's like here. So yeah, let me grab the link real quick. So yeah, I will always upload it onto the YouTube as soon as possible. So I guess as all YouTubers say too, don't forget to subscribe and hit the like button, smash the like button too. But that's something else. I went on tangent again. Let's come back to the materials that the professor lectured today too. So which mostly about linear algorithm and the whole math concept behind it as a simplified version. I try to make it as simple as possible. And if you guys still have like questions on what does each term mean, or I don't understand like the whole concept of derivative and etc., just stop me at any time or put it in the chat or anything. Yeah, I'm happy to explain like the most basic concept. I don't mind anything at all. You can ask me like why 1 + 1 is 2. I'm also happy to answer that. All right, so let's start. So yes, as I mentioned, today we will learn linear regression. But the problem is that what exactly is the linear regression? Well, in simplified word, we want to find the trend line. That's the main concept in like simplest word of it. What is linear regression? But yet we also have the longer explanation from that I grabbed from Wiki too. But yes, also to like try to find the relationship between one or more variables, etc., etc. But yeah, I feel like this is the simplified version that you could understand it easily. So for that definition, let's look at the math behind linear regression. Nah, I don't think that pun works. What's the difference between line and best fit? Line of best fits and linear regression. I don't have the exact definition, but from my understanding, it's basically the same thing. You try to find the line of best fit and linear regression. That's basically built on the same concept. You can use it interchangeably, yeah, but in terms of machine learning, we usually use the fancy word, I would say, of linear regression. Yeah. So let's jump into the math. Let me select the page. So yeah, let's go into the basic concept of math is, if you guys have learned from math, is basically I'm gonna work into the two-dimensional first. For two-dimensional, normally you have a point, right? So the point, you have the x coordinate and y coordinate. So it can be x and y coordinate, right? And for the line, you have line equation, which is y is equal to ax plus b. This one could be a, b, m, or anything, doesn't matter. Or you could even change it to the theta, which professor used in their class too, like theta 1, this is theta 0. Anything could be used as a variable or
Wait,
as a slope.
Nap again. Is
Sure.
it theta or it's beta 1, right? It's beta 1, beta 0, not theta.
Uh, isn't it this
Or,
theta and this
yeah,
is
no,
beta?
but she was using beta in the presentation.
Oh yeah, you could also use beta as well, beta 1,
Oh, okay.
beta
It
0.
works for both. All right.
Yeah, so basically the point is that anything that comes as a parameter, we call it parameter. It could be any symbol. Anything is works fine too.
All right.
I can also use some Thai character too, like this too, it also works too. Yeah. Yeah, mathematicians, they just use all kinds of notation. But yeah, the way, yeah, but yeah, probably something to, I guess we can also something want you guys to, like, yeah, the way I learned it, I usually learn with the data. But if you guys can keep that in mind too, okay, beta, that means I can also convert it to the beta 0 and beta 1 as well. Hopefully that clears off some of the misunderstanding, or I guess something that makes you difficult to understand. But yeah, in terms of line equation, we usually call it as a function of x. So basically you just plug in some number inside to the x so that it will output some kind of number. That also another way to represent the a line equation. So let's say in the full example then. So we have, say we have this line right here. Let me also double check with my note. So this is the, yeah, I think as new, was it new? Let me also check with the chat. No, Nyland. If I butcher you guys' name, please correct me, or yeah, don't mind me if I butcher it. Yeah, so you have some kind of, I guess you can call it like a trend line or a best fit line. Right, and I'm gonna give this equation as f of x is equal to 1/2 x plus 1, right? Which we try to capture the trend line of these data, which I'm gonna put into the square, the red x, like here, say this, right? But we have some kind of question like, okay, so then how do you know what's the best line to capture the relationship of the data, or how do you know that's the trend line or the best fit line? We use some kind of measurement to calculate it, which we normally use the distance from the observed data. So like this given data, we just call it observed data, and our trend line is our prediction. So it's like so then we're gonna call some kind of this measurement of how far off from the trend line, between the trend line and prediction, as a cost function. But you might be to it may be called it something else, like cost function, loss function, or you can call it loss. It doesn't really matter, but the whole point is that it is a way to find some kind of error. So like this is like a way to find how far off, right? So which the cost function normally builds up upon the distance function, or distance, how to find the distance. This like kind of builds on top. But what is the equation for the distance function? Distance function is just some number minus some another number, and you square it. But I want to change all of my letters to match the way that I do this. Like you have some kind of number, which is our prediction, and you have some kind of observation, and we have our prediction, which is fx, and some kind of observation, which is all the x marks, right? So we're gonna call it the cost function. And we have our parameter, which is the slope and the interception that we want to find it for our line. So it's going to be cost function of A and B is equal to, I'm going to call it predicted minus observed. square, which our prediction is the this fx plus blah 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 thing, and we can just simply switch it, switch it within. But I'm gonna write down like in the more simpler term as well to makes it more clear, and you can also like compare it with the equation that you found online or something, which is gonna be a plus, no, it should be ax plus b minus y hat square. And again, as a reminder, the a and b could also put as like b0, b beta 1, beta 0, anything else, or theta 0, theta 1. Anything also works fine. So far, so good. You guys have any question?
Wait, so the y hat is the observed or the predicted?
It's the observed. Yeah.
The y hat's the observed?
Right. We
Okay.
Yeah, normally anything that we put the hat on it, it's the observed or given, which is all of these the X marks over here. So yeah, I can highlight too. So this is predict, and this is observed, and this is observed. All right, so let's see in.
Oh wait, ask again?
Yeah.
I thought doesn't the hat over a symbol, doesn't that mean estimated value?
I might have to double check with the first slide real quick then. But yeah, I don't.
Yeah, I think
could be wrong.
that's what I got away from the slides as well, is that the hat means the estimated value or the predicted value.
I think it like doesn't matter because you square the value, right? So it's the same value either way.
No, just the meaning of the hat symbol.
Yeah.
It matters because the hat like overall means something.
No, but if the y hat was as in the spot where the predicted is and like the predicted was in the observed, wouldn't it like be the same, I guess?
No, I was talking about, I think generally Sam talking about the universal notation that.
Oh, sorry.
Universal notation. Yeah, I should correct me. Yeah, I was wrong with that. The universal version is that you put a hat on the prediction. But yeah, I think from my understanding, Ethan was arguing about like, oh, it doesn't matter anyway because you're gonna square it. So you're gonna put prediction in front or after the minus sign or something else. It's gonna give you the same value as well. But yeah, we're talking about the universal notation, then the hat will be goes into the prediction. Yeah. Thanks for correcting that. Or maybe I should say, I was gonna catch you guys if you guys listen to the lecture.
Wait, so but like general, you write it over the A and the B, not the X, right? Like when you're writing it normally.
Well, technically it's like A is equal to AX plus B.
So the hat goes over the X. All right.
Yeah. Or maybe I could double check. If you in doubt, Google. Regression. Equation. So why that not that. Not that.
So maybe the hat just needs to be on the Y, I think, right?
Yeah, the hat just.
It doesn't matter.
It doesn't matter anyway because I think the hat generally tells you that that's our prediction. So then any kind of x is going to be some kind of input value that we put it in. So it doesn't matter anyway. So we just put the hat on a y, and then that generally tells you enough that that's our prediction. So it could be. Maybe I should correct this into y hat, and that's our cost function is going to be ax plus b minus y square. And our y is observed again. Y is observed and y hat is predicted. Oops. Yeah. Any concern? Comment?
Nope, you're good.
All right. So let's look at the example of how we use the cost function then. Let's see if I can like squeeze these to small size. So yeah, let's look at one example then. So say if we have this point, right, and then this point is given as a point coordinate of let me check. This is 2, 1, which slide onto the x equal to 2, right? So we're gonna find the, so like this one say find cost at x is equal to 2. So we're gonna have cost of a, b is equal to the predicted minus observed, and then you square it. What's our prediction? Prediction is this trend line, which is 1/2 x plus 1 minus observed. But our observe, so generally observe means that what's the output of the x value. So which is in this problem is going to be 1, because x at x equal to 2, what's our observed data at x equal to 2, which is this data of, and it has y value as 1, right? So you're gonna just minus 1 and the whole thing square. And I'm gonna move into another page here. Well, copy everything. And I'll get the data too. Right, so we want to find where x is equal to 2. So we just go 1/2 2 plus 1 and then minus 1 and the whole thing square. So which is just 2 plus 2 minus 1 square, and that's equal to 1. So now we know that, okay, at x equal to 2, we have a cost value of 1. Let me change color as well. So this is cost at x is equal to 2. So now we know that, okay, we have cost value of 2 for now at the moment. So then we want to also generalize that cost value to every observed data. So say we have 5 data point, right? We also want to keep calculating by using this formula to every observed point while using the same predicted function value. So I'm going to generalize that into the cost function of a and b is equal to the sum. This is just the notation of sum value of I. You started from I is 0.1, and you're going to find the value of the prediction at point I and observe I, and you square it. So let me explain it again too. So remember that this example, we just find it at one point. So we just substitute it with the cost function of this point. But then if you want to find like x equal to 3, we also have to substitute this with 3 and then do all the calculation again. So we repeat that again and again and again until you get every point from the data. And that's going to be your cost function of the whole data point, the whole data set, while trying to see how how much far off of the for your trend line, which is your prediction between your prediction and your observed data. But some note, normally people use mean square error. So mean square error, which is just this equation, but we find the mean of the whole equation. So it's going to be cos of AFB is equal, wait, I should say MSE or mean square error is equal to 1 over n, because we find it over n data. And it's going to be the same thing predicted at point I and the observed data point at point I in this square. So that's the whole, that's where the name came from. If you want to find the mean of the square value of the cost function. But in generally it could be any one of them, because you simply just find the average cost of every data. So I just want you to know that there's also like other notation as well, or you can even find like some, if you look up online, there's also some notation, some cost function that has like a 2 in front of n. That's because you want to find derivative, and that's make the math easier, etc. But in my opinion, it just basically divided everything by 2, so it doesn't really matter much anyway, since you're going to scale by half for every data point. But that's just something else. The point is that you want to find the cost value of the line, the predicted line, and you want to, and if you're going to move into the next section, which is you're going to find the cost value that has the lowest value as much as possible. But before that, are we all clear with the concept of cost function and the trend
Yeah,
line?
I just had one question.
Sure.
So on you said I equals 1. So is that the case for all situations, or just because you did the formula like a little bit up where you did x equals 2 and got 1?
Yeah, so technically almost every data is going to be represented by this like data 1, 2, 3, 4, right? And it has its x value and it has its y value. Like this one is going to be like x is equal at x equal to 1. You're going to have like say x1, and I would probably put it at like 2.5. At data 2, which is this one, you're going to have x is equal to 2 and then y value is equal to 1, and etc. etc. Right. So then when we say that observe I, you want to look at their data 1, observe I, and you substitute I with 1 for this one. You're going to go with, okay, what's the x value at 1? What I mean, what's the y value when x is equal to 1? You're going to get 2.5. And then you write down 2.5 in here, and then you substitute x into the prediction, which is this function of the trend line that we have. And then you calculate the error. Is it clear? Or do you want more clarification? I'm happy to explain more too. Silence means nothing. I don't know. I don't want to say yes, because I don't want to assume that you understand it.
I definitely am understanding it a lot better now.
Right. Cool.
Yeah, me too. It's really clear.
Okay, nice. Thanks. So yeah, when we so from the whole concept of the generalization is I want to generalize the concept of the linear regression. So normally ideal data and trend line, I would say trend line just for now, but when you talk about the whole linear regression, normally you just use the word regression. I use the trend line just to for you guys to easy to understand. But yeah, if you talk to other people, use the word trend line. No, use the word regression. So say this is our trend line, our best fit line, our regression. Let me do this. Normally we want something like this, that we have, say we have data. let's write down. So suppose there's the data like this, right? And we want to find the line that goes through every point that cross every observed data point. So what does it mean? If the line cross every data point, it's gonna give you the overall cost is gonna be equal to 0, right? And that's the ideal data and ideal regression that we want to. But in reality, it doesn't really work like that. It has some kind of outlier, and then the data is spread all around. So something like this, like we have all the data spread around here, and maybe some here too, and something like this. And supposedly, if you find the best trend line, the regression is going to give you something like this, right? But so then when you find the cost function of this one, it's not going to be 0 anymore, because there are some descent from the data point to here at every point, right? But what if you, but in another extreme case is that you also do something like this, like you have another line like this one. But from observation, you can see that the distance from observed data to the green line is definitely much more than the cost function of the blue line. So this one has to say like the cost maybe of this line is not equal to 0, definitely, but seems worse than the blue line. Right? So then this is going to become into the main goal or motivation of why do you do all the derivative and find everything. So then that we learned earlier in the morning. So then our goal is that we want to find a line which we want to find the parameters of A and B. So we want to find a slope. We want to find a slope of a function of the line function. So don't forget that we have fx is equal to ax plus b. So we want to find the line, or we want to find the parameter A and B such that I'm just going to write down into it just st. So that's going to be such that the cost value of A and B give us a value as close to 0. All right, that makes sense. Maybe you can get thumbs up or PogChamp in the chat. No, probably just I just unveiled like yes, no, or anything, any clarification that you need.
Wait, Nathan, what does ST mean? Because you say we want to find a line AB.
Such that.
Huh?
Such that ST is just equal to such.
Okay, thank you.
That, yeah. No worries. Yeah, that's just asking you any question or anything that doesn't make sense. All right, I'm gonna move over then. And if you still have any question, yeah, I'm gonna probably turn at the end of the class, you just turn this into office hours, and I can also clarify anything more, or you can also come to my office hours on Saturday or Sunday. So yeah, I think as Neil also said, like, what's the difference between best fit line and linear regression? In my opinion, it's just the same thing. Like, I'm pretty sure if you take some kind of physics class or some kind of science class, just go through the Excel and find their best fit line, right? And then get this. So remember this. This is it now. If you saw yet. So yeah, this one is also from the online course from Andrew. I think just for some kind of clarification, we can also substitute everything like theta 0. We can also just go with b plus ax. So parameter is going to be the same thing with the y-intercept, and the slope of it, right? And cost function, you just hx, I mean h theta of x is, this is just predicted. My handwriting is so bad. Predicted. And the y is going to be your observed. Right. And our goal is the same thing.
Wait, Nathan, when it has the superscript I over the x and y, that's that individual ordered pair or that piece of data, right?
Correct. Now you got
All
it.
right. Thank you.
Yep. I like this. Yeah, you guys catching it quite fast. Yeah. So yeah, as I said, the goal is to minimize the cost. So this is cost function. So yeah, let me
So
reiterate. Oh, you go ahead, Mark.
Is J the cost function, or is that like how? Because I think she used L in the, like, how do you know what the symbol for cost function? Because I think she also used L in the slide. So J or L, either one.
Yes.
Right.
Yes. As I said earlier, we can generally people call it differently. Sometimes some people call cost function, and some people call it loss function. And loss starts with an L, so people just use the L of 0, theta 0, and theta 1. Or if you use professor notation, it could be like L of beta 0, beta 1. Basically, that's the main. That those two things are equivalent to each other, but they just haven't come up with like the a standard, I guess, standard name for it. So people just call it whatever they feel like. But yeah, if you see like the loss function or cost function with L, either L or either J, but the thing is that you want to look into the equation as well. Like, okay, so then if this equation has something like this, then that's mean that, okay, you want to find the distance from the observed point to your trend line or to your regression. But in a broader way, I would say, yeah, you just have to keep learning or keep looking at the equations until you recognize that, oh, people use J or people use L. So that means that it's a cost function or loss function. Yeah.
Okay. Thank you, Nathan.
Yep.
I also have a question.
Sure.
What is the h theta in the cost function? Because originally, like when you did the problem, it was like 1/2 x plus 1. So is that still the predicted?
Yes, it's our prediction, which we can, yeah, in our example. So in example, we have like a is equal to 1/2, or we can also use the theta 1 in this example of b is equal to 1 in this theta 0, right? But the problem is that we yes, as I said, we want to find the goal. The goal is that we want to minimize the cost function, and by keep changing a and b, or so-called parameters, we want to keep changing the parameters so that the line will be regressed to the observed data and give you the lowest cost value. Does it clear up, or was it clear?
Yeah, that makes sense.
Yeah, so that's gonna be the next section, which is how to find A and B, or how to find your theta 1, theta 0. Which is, yes, as I said, but how do you get from this? Like, so this one, in the slide, he gives like A is equal to negative 0.1 and B is equal to negative 400, right? But then we want to change it to something like A is equal to 10, B is equal to 150, something like that, right? But how do we know that? How can we change it from the left side to the right side? So then we're gonna use something called gradient descent. And this is gonna be fun. All right, let me also explain. Get that new page. All right, so let me just move my screen a little bit too. All right. So many things on top of my screen. All right. So reminder that we have our predicted line, which is fx is equal to a x plus b, right? But so as you also said, the goal is change a and b such that the cost of a and b is almost close to zero. But I'm just gonna generalize it that you want to make it as close to zero, but in reality, it sometimes like 1,000 could be the lowest that you could do, but that's also something else that I will explain later. But yeah, just for simplicity, we can say make it as close to zero. So then, how can we change the parameters? So I'm gonna put some notation. So it's gonna be a of. So this is gonna be some kind of like programming when you assign new value into it. So I want to change, say I want to change a, right? I want to change a by having some old value, and you want to do some math operation within it, and then assign it to the new variable. Or if we can just gonna keep changing with a, and we're gonna do it the same thing as b. I'm just gonna copy this. B. Right. So then let's do some constraint or some example. This one, suppose b is already optimized, or we already find the base value of b already, and we have some example of this, like, and we have the observed data like this lies on that, right? And then goes back again to the example, to the thing that I mentioned earlier, if we draw the line on top of every point, like right exactly on top of every point, right? This one gonna give you the cost is gonna be equal to zero, right? So then, how about we draw another graph that represents the cost value of every point? So this is cost graph. It's gonna be this. And say every time we want to change the slope of it, cost graph of slope, which is the a. So this is gonna be the x-axis is gonna be a, and the y-axis is gonna be cost value, right? And suppose this line is f of x is equal to just 1x, right? So now if you draw the line on top of the data, and we get the cost function is equal to 0. So we make a graph of it. So instead a is equal to 1, the cost value is going to be 0, right? Make sense so far?
Yep.
All right, cool. And say if we don't know this line, right? And then we just randomly draw the line, say like here, and this one is like f of x equal to 2x, right? And then and it's the same thing. You find the cost distance and keep calculating blah blah of every point, and then you find like this is just a random number, okay, but it doesn't really reflect the true value. But say if you find the cost value of this one is equal to, but it's definitely not 0. So let's say like 2 or something. So then at x, at a is equal to 2, the cost value is going to be the cost value is going to be 2. So let me also graph this into the cost value graph. So it's 2 at 2, then cost value is going to be 2 right here, and then you plot it, right? But then again, if you make the line further steeper, right? It's going to go into the same thing of, okay, but that also means that the distance from the line, between the line and the observed data is also goes beyond further and further. So this one says supposedly like the cost function of f of x is equal to 3x. So say this one gives you like 5, so like here, right? So at 3, it's going to give you 5, but I don't have point yet, 5. Right. At the same thing goes to the other way, right? We make it steeper and steeper, but we can also make it goes down like this one too, which gonna be like say f of say this line has its own function which is 1/2 x. So it's gonna have some cost value too, right? And definitely it's definitely not 0. So this one says supposedly like 1, give you cost value of 1, right? So at 1/2, you're gonna give like 1. And because if it goes like 0, which is just a horizontal line, you're also gonna get some distance that further down, and definitely further than this one. So like at 0, you're gonna get like, I could say like 2 again, doesn't matter. Yeah. So you keep drawing, keep plotting it by changing the slope or changing a to almost every possible number. You're gonna get the graph that looks like this, right? But then we can start to see like, okay, from the graph, I can observe that, yes, I want to get this from this, I want to get the lowest cost value, which is 0 in this one. And what's the a that will give you the cost value to 0, which is 1. That's going to be 1, right? And if you want to find the minimum of the graph, so the graph looks like this, right? If you want to find a minimum of a graph, use derivative. So in case that you also are not familiar with the derivative concept, so like in the simplest word for me is that derivative means that finding slope of a graph. Okay, so for example, from our example is this, right? We want to find the slope of the graph at a particular point. So if you look at the very bottom, if I like zoom in, it's gonna look something like this. So you're gonna be probably like, it's not good. Yeah. So this is at a is equal to 1, right? And you want to find the slope at this point, which is going to be roughly horizontal line. So that's the whole concept of the derivative, is that you want to look at particular point and find the slope at that one particular point. And with calculus, we know that if you find the derivative and set it to horizontal line, so which is going to be 0 in this case, so this slope is equal to 0. That's going to give you the minimum of your graph. And since you get the minimum of your graph, that means that you also get the minimum of the cost value. And if you get the minimum cost value of your parameter A, that also means that you will get the optimal trend line, optimal regression. Make sense? Or do you want me to further clarify it more?
How would you like find a derivative then? If it's not like a normal function, if it's just like a bunch of points, how would you try to go like finding the slope? I guess.
Let's see. That's the question is kind of like cover lots of things. I try to like, I don't know. I'm thinking how can I like narrow that down. Yeah, that because your question is also involved lots of things. Like I think you also say like, oh, if you have like this kind of slope, or if you have this slope, or no, how do you find like the slope of this, right? Is that like also something that you ask? Or,
Yeah, I get something like that. Yeah.
yeah. Generally, you take, so like for this case, just take derivative. That's also another way to do it, but this one I can just like goes with like one is the simplest solution. So one solution is that take derivative at every point, and then find which give you equal to 0, right? And then you get like two numbers. Say this one is 3, this one is like 10, right? And then you're gonna plug that number back into the cost function, but it's gonna give you a different cost function as well. So like for yeah, it's gonna be too complicated. But
It's
yeah.
okay. I think I got it.
Yeah, in the simplest way is that you just take derivative of it and then find the point that the slope of that particular point equal to 0.
Okay, thank you.
Yeah. But if you want to look at more, maybe there's gonna be some kind of algorithm later too from the slide, right? And then I can say like this. So the goal is everyone to set the slope, and this one is gonna be some notation of finding the derivative, and then you set it to 0. So when I put the triangle, just set it to 0. And then back to the beginning point that we're talking about.
Oh, wait, sorry. Wait, how do you take the derivative of something, by the way? Or how do you take the derivative of the graph?
That's like the whole math of finding calculus, but yeah, because there's also different kind of finding the derivative. So like, for example, this one, x to the n is gonna, the derivative of that is gonna be n to the x of n minus 1. Like cost function of x is gonna be sine, no, it's gonna be negative sine of x. But yeah, that's something that you're gonna have to like learn from the calculus and then memorize it by yourself. But the whole point is this, is that you don't need to like know all the mathematics of how to find the calculus and find the derivative. The whole goal is that you want to know that, okay, the concept of derivative is that you want to find the slope of every point, see every particular point in the graph. And our goal is that we want to find the derivative or the slope such that it gives you a 0. And that's going to be your optimized parameter for your line function. But yeah, I guess don't worry about it. That's going to be my catchphrase. So yeah, don't worry about it if you don't understand. But yeah, that's like another stuff. Because I think our goal is that we want you guys to kind of have some understanding of why does that make sense, but you don't have to like memorize everything. It's just a memorize through, and then at some point they give you a function that you can resolve using a graphing calculator. Anyways, yeah, as Ainsley said. And we have computer, so why not just use computer? But that's also like some kind of debate too. That if you only use computer, then how do you know like that's the correct solution? Blah blah blah. But yeah, let's go back to the slide. So as I mentioned earlier, right? We want to you want to get some kind of prediction, and we have A and we have B, right? And then you want to change the A and B such that you give the cost value as close to 0 as possible. And I have this here. It's going to be some kind of A, the A value of the old one, and then you do some operation to it, and then you get the new one. So that's going to be, like I mentioned, it's going to be some value is equal to slope. And then, and we're going to put in some parameters in here so that it will, this is just called something called learning rate. But for the simplicity of the sake, for the sake of simplicity, I'm gonna set it equal to 1 for the moment. All right. So let's see how that works in action. So say we have the cost function, right? As we had earlier in this example. Say you started from like f of x is equal to 3x, right? You're gonna have this, and you're gonna get, so basically you're gonna get at 3x, you started from here, right? So come to this one, you're gonna start it from here, right? And this one gonna give you some kind of slope. I just put it some random number, right? So slope is gonna be 3, for example. And then imagine that, so like, let me go back to the whole update stuff. It's gonna be a new is equal to AO minus lambda, or lambda is gonna be lambda, and then times slope. So right. So say if you have, so now AO, the old value of A is gonna be 3, I believe. Let me get that. Okay. Haha, I feel you. I feel you, Stephanie. Okay. So we have that. So say we have the slope of 3, right? And then you have the order value is going to be 3. So we substitute back. So 3 is going to be 3 minus. So I just set it learning rate to 1 for the simplicity, and then slope is going to be 3, right? So now the annual is going to be equal to 0. So basically you travel back down to here at A is equal to 0, which is already our optimal value of A. Wait, no, shouldn't be. The example was 1. Sorry, I forgot. This is A0. A is equal to 0. Yeah, so basically you goes from here, you update the slope, and then you traverse down here at A is equal to 0. And then you repeat it again. You substitute back A of old, and then you get some slope. Slope is gonna be like, so this one is gonna be the negative slope, right? So it's gonna be, say, something like negative 0.5 for this one. You're gonna get like, gosh, there are too many stuff. So like A new is equal to A old, which is 0 minus learning rate is gonna be negative 1, and then negative 0.5, right? And then calculate it, you got 0.5. So now you're gonna, gosh, this is so messy. This is A is equal to 1, A is equal to 0, A is equal to 0.5, right? And then you also come back to here, this value. So from the algorithm, you kind of observe that, okay, if I do this, you're gonna keep going back down until you reach at the bottom, which gonna give you the slope of this point at equal to 0. Does the learning rate always 1? No, we don't know what the learning rate is. That's gonna be something that you have to experiment and try to change everything. But yeah, the whole goal is that this is how the algorithm of gradient descent works. Is that you want to update You want to update the value by finding the slope of the graph and then update the old parameter with the new one, with the hope that you keep going down to this bottom point, which will give you the optimized parameter. And with the optimized parameter, will give you the best fit line or the optimized regression. Is it too much? Do you feel like understand it? Get it? Yes? No? Okay? Man?
I get it.
All right. Anyone else?
Yeah, I'm good. No problems here.
All right. Cool. So yeah, that's gonna be the whole art of it, which is the whole algorithm of it, which is you to make it generalized of it. Update every parameters. So there's not gonna be a of new. It's gonna be a for minus lambda of slope of A, and then B, the new B is gonna be O minus lambda of slope of B. That's the whole logistic of it.
Oh, so in stochastic, that means that the lambda will change, right?
Yes, well, I don't have the exact definition of stochastic if I on top of my head, but there's also like then another way that you can like. So let me go back one step. Okay, so like earlier we have like lambda is equal to 1, right? But say if the data is like this huge, like you have like you started from 1 million, right? And then 1 million, right? And then if you go with lambda is equal to 1, it's gonna keep going one at a time like this, and it takes forever until you reach the optimal point. Or if you set lambda too high, like 500K, it's gonna keep shooting over here, and you never reach the optimal point. And there's also some kind of parameters that set lambda is equal to some kind of you do something with, you also take the slope, and then I don't remember the math exactly, but yeah, you do something with the slope, and like you see like, okay, if the slope has this much of this much of the value, like 10, you also go with the 10. But if you go to the 1, if you reach like to this point, change the lambda is equal become 1. That's also like another.
So
math
lambda
equation.
changes in like proportion to the slope.
Yes. So it's gonna be like, so the whole thing is gonna be something like a minus lambda and slope, and become like 8O minus slope times slope. But this is not the exact math equation, okay? Yeah, you might have to like look it up further. But then I just explain it in the really simplest term. But yeah, but in my understanding, stochastic is something different. If I have to be exact, but I have to also double check with it later too. But yeah, phew, that's a lot for stochastic gradient. No, gradient descent. So like here, let me show you this. Like, let me also change to my PowerPoint real quick. Give me one moment. It's like here. I don't know how Zoom screen share might reduce the frame rate of it, but this is like the whole graph to visualize how the cost function is going to be. Like you randomly start at a position, and you keep going down to the slope, and you're gonna want to reach to the bottom point of the slope, and your line is gonna be keep changing until you get the best fit line. That's gonna be the whole algorithm of gradient descent. Cool.
Yep.
All right. Yeah, and if you go further, like this one is also, as I mentioned, like what there's also multiple location of the lowest cost, the cost function. There's gonna be like this point, blah blah, and there's a lot of them. Or it might be like something as crazy as this. Like you have so many things and you don't know where to start. And you can, in order to find the local cost value, you can also repeat the trial again and again with randomly as initialize the starting position, and in the hope that if you started from like this point, you're gonna get a new data, rather than you keep doing the same point position and again and adjust the running rate a little bit. Yeah, so or basically you want to start at random point and hope that you get the lowest cost value, which I should double check if the stochastic gradient, from my understanding, is the same as the other. But yeah, that's like the whole art of how do you find the lowest cost value. And I don't know if that's something that I could go beyond. But yeah, how about we take 10 minutes break and we'll come back with linear regression with multiple features. All right, see you all in 2:16 then. But yeah, meanwhile, I'm happy to also answer any question. All right, it's 2:16, so I'm gonna keep continuing with the discussion. So yeah, let's do a little bit of recap with everything so far that we have done. So we trying to learn the linear regression, right? And then we're trying to find the optimized parameters, or we want to find the best fit line. But how do we find the best fit line? We want to optimize our parameters. How do we optimize our parameters? We use gradient descent. But what is gradient descent? Gradient descent is a way to find the slope, and you update your parameters. And that's the big, I guess, big bubble of the linear regression and how it works, so that you can get the best fit line. But in earlier example, we simply use the simple equation line, which is y is equal to ax plus b, or y is equal to theta 1 x times x plus theta 0, or beta, or anything else, like, which is this equation. But in reality, the data is not only simply just like one variable, which is x. It's gonna have like x2, x3, x4 up equal to n, xn, and you can kind of like imagine x as some kind of feature. For example, if you want to calculate the BMI, right? You want to get your height, you want to get your weight, etc., so that you can get your BMI. And that's the same thing. You also have other variables or other so-called features that you want to include that. And this is going to be the generalized equation for linear regression with multiple regression, with with multiple variables and parameters. So here, if you can see some similarity between it, you have like y is equal to b0 plus b1. Well, you can just think you can also just go with b, or this one can be a, or which is also same as beta 1. It's just basically it's just a symbol to symbolize the parameters, and you have this whole thing, and you have other features, and each feature is gonna have its own slope as well. So if you visualize it, it's gonna look something like this for the 3D equation. So it's gonna be this equation. Let me get this. Y is equal to. Let me also try this notation so that you guys can also be familiar with it. B0, B1, beta 1, x1 plus beta 2, x2, which is going to give you a 3D model. And this one, for example, is going to be this feature, and for x2 is going to be another feature is over here, right? So this is so basically we can further expand the linear regression to multiple linear regression. And if you have multiple regression, you can also, so like this one, you have one feature 1, feature 2, feature 3, right? But at the same time, you can also have feature 1, and then you square it, and then feature 1, and you raise to the power of n as well. So this thing are gonna be the same. And why do we have that? We have that because sometimes the data will look something like this. It's gonna be a curve rather than a straight line. If you go with the straight line, the best that you can do is gonna be this green one, which is y is equal to beta 0 plus beta 1 x 1. But it doesn't capture the data that well, right? So then you would have to find some more complex model to get the best fit line. So then this one can be something like y is equal to beta 0 plus beta 1 x1 plus beta 2 x1, and then you square it, right? So yeah, just keep in mind that the subscript tells you the tells you the what is the feature. The superscript tells you what's the degree of it, or you can square it. And this one, technically, this one is gonna be like b2 x1 times x1. Sorry, something like that. All right, and then if you're gonna further expand the dimensionality, or AKA you add more variables. The same thing also. The same thing is also applied for the cost function or loss function, as well as the gradient descent. You just keep finding. You just go within that feature and try to draw the cost function, and then find the lowest point, and then you update it, and then keep updating that until you get the optimized value for each of them. So far so good. Yes, no. Okay.
Wait,
Kinda.
so I think I kind of just blanked for a bit, but
Okay,
for this
no,
part, you're basically just doing the gradient descent for each like variable at a time to solve for each of them.
right. So like for
Okay.
from our previously, you have a new is equal to AO, right, minus this and slope, the lambda times slope, and then as well as the B is equal to B or minus lambda slope, right? But if you add more feature, that means that you but if you still have old equation and add more feature, then how are you gonna update the leftover feature? So basically, you just do the same thing with the leftover feature, and then so that way you can get to the lowest. You can get the optimized value of the feature. I think maybe some kind of this analogy, like, right? So say if you're on top of Mount Everest, right, and but you want to get down to the village. Technically, if you look from the bird eye view, right, you're gonna have the x value, x-axis, and y-axis. You're gonna keep going. You wanna try to go to the lowest point, which you're gonna try to reach the village, right? You're gonna go to the right by optimizing the right value or the x value, as well as optimize the value of the y-axis, which is your like forward or something. Yeah. And in this case, you're gonna separately calculate each direction. So you want to hope that you go to the right, you get the lowest point. And at the same time, you also go down and forward or backward to the lowest point. And then you keep calculating each one, and then sometimes it's gonna be some kind of slope that like goes just goes steep, like directly in front of you, but the right side is gonna be like just keep paralleling, right? So you're just gonna keep going down instead of going keep going to the right, something like that. That's gonna be like analogy of how you find a gradient descent to get the lowest cost value while you have multiple feature. Does this analogy make sense?
Yeah, that was helpful. Thank you.
All right, cool.
Wait, I also have a question.
Mhm.
For this, is this just a different loss function where it's multiplying x subscript 0 or x subscript 1? Like, why is that there? It's just a different loss function, or
Oh, it's the same loss function, but here, let me also. This is loss. Is this loss function? Wait, this is loss function. hope that you guys get it. But anyway, yeah, it's a same
I
of
can't
loss
believe,
function.
why have you done this to me?
Gotcha. Got it. Yeah.
You've ruined my day.
Don't tag me, okay? But yeah, let's go back to this. So remember that the loss function. Wait. loss function is the or mean square error. Basically, it is 1 over m times the sum of over the point, and you're gonna be predict. I'm just gonna write predict of I minus. Let me just go with the new page. But yeah, I guess like short answer, that's the same. That's the same loss function that we use. And long answer is that that's gonna be the derivative of the loss function. I just want to work out a little bit to you. Like this is gonna be prediction minus observe phi, and then square it. And then the way that you find derivative is that like you don't have to memorize this. I just want to show some like little bit proof of it. Like so, this one, the derivative of x over n is gonna be n of x minus 1, right? So then if you have 1 over m, which is I to the m data of prediction of I and observe of I, right, square it. We want to, but our prediction is basically f is going to be f of x is equal to a x plus b, right? You substitute that, and then you take the derivative with respect to the parameters, which is just a. So like derivative with respect, so to a, right? You're gonna get something like 1 over m, and this whole sum still is, this whole thing still the same. And you see the power, you just bring it to the front, right? So it's gonna be 2 times 1 to the m, and then the whole thing as observed. And then the power will be gone because the 2 is gonna be 2 minus 1 is equal to 1, right? But there's also some term of it which, again, I don't expect you to memorize or know that everything, but in case that you're also familiar with the calculus, so you also use the chain rule to find the coefficient of a, because we take derivative with a, right? But there's still a coefficient of x, so this is going to be x. And let me also do some
I get it. Now
similarity.
it's the derivative of the loss function.
Yes, yes,
All right.
yeah, in the short version, short answer, yes, this is the derivative of the cost function, which is our slope. And
All right.
I
Thank
just
you.
use this word slope. Yeah, no problem. And then that's why you have some kind of x. But yeah, generally, the whole point is that if you have if you want to find gradient descent, you would just keep find gradient descent of each feature and then update it.
And then that alpha value is just like the learning rate, right?
Yes. Yes.
All right, perfect.
Yeah, any Greek letter like alpha, generally, yeah, people use alpha or lambda, but the whole point is that that's the learning rate. And yeah, also again, be careful with the learning rate. Sometimes it's easy for you to set the learning rate too much or too low, but the question is that how do you know what's the ideal learning rate? That we also don't know. That's also something like I think it's on a research. It's also some kind of research field, but I'm not too familiar with it. I just heard it from somewhere, but yeah. Because like if your features like scale of 1, but then you use learning rate as like a million, then that it doesn't work together. So then you have to like experiment by yourself. Yeah, that's like some rant with that. So okay. Yeah. FYI, the rest after this, I think it's gonna be more of the tomorrow's professor lecture, or maybe next 2 days. But I just want to also like, give you guys a little glimpse about it so that you're familiar with the concept of it, right? So from the last example, I introduced you guys to the multiple linear regression, but we also have polynomial, which is just use the same feature, but then you square it and you raise to some kind of power. And sometimes it is easy to you to just simply say, okay, just use simple linear regression, right? Like y is equal to ax plus b, and hope for the best that it will capture the data, but then it doesn't capture the data that well. So we call it underfit. Or sometimes you just use like, oh, how about I just use x and then raise to the power of million. So you just keep iterating like x1, x2, x3, and then plus blah, blah, blah until x million, but then it's going to keep overfitting. But then if you get like some kind of data point, a new data, like somewhere at here, right? You're gonna say like, oh, but the line said that it keeps going up here, so then it doesn't really work that well. So then you want to find the right balance, that you don't want to go too underfit or too overfit, and find the right balance that you have a good fit, that you capture the data, the data point. And that's gonna be something that you want to try it out with different. So basically, this is just a trial and error. You just try different thing and see how much this, how for each model or each equation perform, and you just keep doing it until you find that it does the best equation for the line. Or another way is you can also visualize it, but that generally works for like 2D data or data that has 2 features, but sometimes you can have like 1,000 features which you can't really visualize it. But yeah, that's like something for you to know beforehand. Yeah, there's some like terminologies and tips. Let me see if I should go over this stuff. Maybe I can talk about it like tomorrow or later about bias and variance. But this is, oh yeah, FYI, if you can also read the slide later, but I'll probably go over it tomorrow. But yeah, FYI, for the word variance in this case, it doesn't mean the same thing as variance that we learned like from the lecture, but like, oh, how much does the data deviate from the mean data? That's like not the same variance. But we also sometimes use the term bias and variance to explain how well they perform, how well is the data perform, does the model perform. Like if you have underfit, data, you're gonna have high bias, but low variance. But if you have overfit, you're gonna have overfit model, you're gonna have the low bias and high variance. So this is the visualization. But again, I think I'm gonna explain it further for tomorrow because I don't want to get too far ahead. And yeah, another thing is that another concept that I also want to introduce you guys is the R squared, which is another way to show you how well does the model capture the trend line, or no, sorry, how well does the model perform and capture the data set. So R squared is the goodness of it measure for linear regressions. So basically it tells you if the R square is around 1, right? That means that the car age and price goes together. But if R square is right around like 0, that means that 2 variables are not correlated, or it doesn't go together. So like it kind of spread out like this. And R square tells you that if you have the model, then means that this model, if this model is equal to like here, this one we have example of 0.08, that means that it doesn't really capture the data well. Meanwhile, this one, it has the R square is around like 0.95, right? So then it captures the data well. That's also the concept of the R square. And this is also another example to show the value of R square, right? R square, this one is also this one R square has a 0.81, which is the blue line, and it captures the data well. While if you change the feature to like something else, so this one you have the mouse size, but this one you have the time spent sniffing a rock. The model doesn't really capture the data set that will, and it doesn't really tells you well with the mouse weight. So mouse size, this one you can kind of infer that, okay, then the mouse size tells really gives you the models that explain how mouse weight and mouse size are correlated together. But the mouse weight and the time spent sniffing a rock give you low R square value. That means that these two rarely have just a little correlation to each other, but it's not as good as the mouse size. But yeah, and also like if you also be careful with R squared. If you have like too much of R squared, that's also mean the models are overfit as well. So that this one is gonna go. If you have like R squared is equal to 1, you probably want to raise the eyebrow like, no, that doesn't really work. That means that it captures everything, but it will be too overfit. And then when you input a new data, it doesn't really the data from if you input in the new data and then you try to find the cost function with the trend line, it's gonna say like, oh, it doesn't really work if you use this overfit model. Right. And yeah, basically when you're working with the data, you also try to consider the features correlation as well. And sometimes you want to drop some feature that you feel like it doesn't really contribute to the prediction model. For example, say if you want to predict the price, right? But then you have ID and you have some kind of say host ID, which gives you like 0.1. You might say like, oh, if that's gonna give, if that's not necessary, then maybe we can drop it. But that's also something for you to decide. Like, oh, that could be necessary if I modify it a little bit. Or you can say, oh, it doesn't matter. I can just delete it. Yeah. But yeah, that's a lot of math for today. But hopefully that's the bottom point is this page is that you generally use the linear regression to find a trend line or find a best fit line, so then we can make a prediction of a new data point. And you use the model that you use shouldn't be too overfit or too underfit. And R-squared score is a way to find the model's accuracy. And yeah, now you see the math behind it. I want to also give you a little lab for you guys to play around with the Google Colab, so that you can see the data in action. Let me also get the link, and you guys can go to the Colab and see how it works. Let me grab that real quick. Oops, it just break the line. Let me do this. That should do it. Yeah. But let me also share my screen, and then I can also go step by step. Give me 1 sec.
Wait, yeah, can you actually go step by step
Sure,
through it?
I can do it. Yeah. All right. Hope that I get the right screen. Let me do that. Yeah. Should be correct. All right. So let's also sign into that. Wait. I'll change my screen just in case that there's some sensitive information. But hopefully not. Yeah, meanwhile, you guys can like go through the. Meanwhile, you guys can go into that Google Colab and make a copy for yourself. Generally, it has to collab, but I wonder if I should go with the another one. That one we have a second one which really will have you work on the pandas data set, but amongst TA we think that that's probably too far ahead. But let me also check with the others as well. Give me like 1 minute. I can just do it. But yeah, that's gonna be 2 collab in total. But for this one, let's see the linear regression in action, and then you're gonna see the code and you'll be like, oh, well, I learned all this, but then you can just do everything within the single line. That's why should we learn this? But yeah, I feel the same way too. But if you don't know like the math behind it, then you're not gonna know like which one will have which what are the codes or which data, which model that is gonna be most optimized for you guys. So that for this one, you can just generally run it and see how it goes. But I try to explain a little bit with each data point. I mean each code section. So this one you just want to, oh yeah, feel free to like watch it later too. If I going too fast, because it's 2:42. I don't want to also like take it too long too. So yeah, this one you want to import the data, and then you want to read some CSV file, which is from this link, and then you want to split the data into the x value and y value as we also use it earlier in the class, like y is equal to ax plus b. And
Wait, are you sure?
Nathagan, it's not sharing. You're on
dang
the
it.
slide still.
Oh yeah, sorry. Thanks about that.
No problem.
Yeah, that's why yeah, feel free to correct me everything. Yeah, but yeah, good job, good catch. All right. Cut that second take. All right. So for this code, I have tons of code inside of it, but generally you can just simply just play it and just run it. Right. This one you just import the data, and then you import the libraries. This one you import the libraries, and then this one you import the data, and then split the data. So this one you split the data to the x value and y values, right? So it's gonna be something like y is equal to ax plus b that we learned earlier, like this one. And normally we also want to split the data into 2 parts, the training part and the testing part, so that you get the model from the training part. And then once you input the test data, you want to see like how does it perform without model. So this one is train test split. And again, I don't expect you guys to also memorize everything, because the way that we all struggle is this SK. So if you use sklearn, how to split test data, something like this, like, and you just count like this. Oh, sklearn, model selection, test, train test split, and you just go into the link, and it shows you all kind of explanation, and then you can also look into the example and say how do they use it. You use this line to import the data, and then this one to like get all the data, and then split it into the train data and then the test data, etc., etc. And then you can optimize it by changing the parameters. But yeah, the high level concept is you want to split the data, right? And then you run it, and you will split the data. So let's see how the simple linear regression works for this case. So you say you have y is equal to ax plus b, right? And then you simply import the linear regression model, and then you fit the x value and y value together. So instead of like having us to input the data and calculate everything, you just call it linear regression, and then you fit the data and then let the libraries do the work by yourself, right? The file was up there remotely, or yeah, you guys, if I'm not sure it's on my side, but yeah, probably you guys I want to ask you guys maybe save a copy in your drive instead. Or you can just watch me for now and then try it later. But yeah, generally, please save a copy in your drive. So yeah, that's again, we create a model and we just input the data into the model and then let it do everything by itself, and then you plot it out, and it shows you this line. And in this case, as a reminder, this line seems to be underfit, right? It doesn't really capture the data well. It just goes as a straight line. So then how about we change the data to change the model into this model? You just go with the polynomial features instead of the linear regression. And you can try to change the degree in here, this line. This one I just set it to custom degree to 2, right? So it's gonna be b plus m1x plus m2x squared, and then that's it. But you can try to change it and say if you go with square, it's gonna give you this data type square, right? And then you're gonna get the R squared score of 0.91. But if you change it to like say 4, it's gonna give you another model that tends to capture the data better than the square, right? And give you the 0.99 R squared score. But if it goes further beyond like 10, it's gonna give you the data that's like give you the model that looks kind of weird. Let it run a little bit. But yeah, this one can give you the perfect score, which is 1.0 of R squared score, right? It captures the data well. But then when you use it with the test data, say if the test data is like line it right here, it will tell us that the model doesn't really work well. So that's something for you. That's some kind of like visualization, I would say, of how the model can underfit, it can fit it at the right position, and how it can be overfit. And if you try to predict the level, so say the level is like range from 1 to 10, right? You can try to go like, okay, what if the position level 5, how much is salary does it show? So it's this much. And say if you go like 11, it's this much. Yeah, that's like how an example of how you do it in Python. Of you just input the data, but you don't have to like worry about all the stuff like readiness and choosing language, etc., etc. It will do everything for you. But the downside is that if you want to optimize something like say the lambda or the learning rate, you can't really have much of the room to modify everything. So I would say generally in terms of like if you want to do it in like the everything by yourself, and so you have more power, more control, you would use the NumPy library and then do all the math equations that we just went over in the discussion by yourself, and then try to do everything from the bottom. But generally, yeah, you can just use the public libraries that they already provide everything for you, because we all just want to learn like how to use stuff and build some kind of application. But yeah, try to play around with this notebook, and BTS also provide another notebook, Jupyter notebook as well. Let me grab the link. Give me one sec. But yeah, if you don't understand like the code or anything, as I also said, don't worry about it. You can try to like go. You can try to go to the code and try to read line by line, and then Google like say how does it work and what you do with this and that. But generally, there's going to be some kind of example online that you can just use it. Give me 1 sec. Let me get the link. Someone may change to their data. Anyway, I can do it again. So yeah, I'm gonna put the link in the chat, and I also put it. Hopefully, VLTA will also post it on the CCLE, and you guys can also look at their worksheet. This is their worksheet that we also provide for you to use the linear regression. And I'll go like step by step with it. But I guess in the meantime, let's take a break, shall we? Let's come back at 3 p.m. And meanwhile, you guys can also go stretch and maybe take a look at the recent notebook that I sent you earlier as well. All right, let's come back at 3. All right, it's 3 p.m. So we shall continue then. I guess for the rest of this is I want to ask you guys. I don't know how this kind of works, but maybe I can get you guys feedback later. But the point is that I want to try to do once you guys look at me and look at how I try to solve the problem with and the way how I think about it and the way how I can solve the problem and suddenly get into the final code and get the result. So rather than like having you guys type everything after me, maybe I can ask you guys if you guys I want to ask you if you guys can look at me and just listen to the whole thing and listen to the whole process, and then you guys can like type it in later after you watch the recording or after you get like the look into like the whole full code from the CCLE. But otherwise, if you feel like you can also follow my typing or anything, you can also just do it too. Or if I go into like some kind of function or some kind of concept that you're not familiarized, you can also feel free to stop me and then ask me to. I'm also happy to clarify everything. But the main point is that I want to show you how I work so that hopefully you can get some sense of how you can also apply to your to your either homework or your project too. All right. So let's see. So for this, you can see that this one you get the data from here. You can just download it, and we give you this data, right? You can either download it. So there are two ways that you can do it with the avocado. Oh no, not avocado. With how you import the file into the Google Drive. The first one is that you just go to the Google Drive, right? And you simply drag your file into here. And then once you upload that onto your Google Drive, come to here and then write down from google.collab import drive, and then drive mode. It's going to give you set in the drive, right? And then you get your authorization code, etc. Let me see. Yeah, should be fine since it's going to be two-factor authentication anyway. But yeah, once you get there, you might ask you for some authorization code. You just simply copy that down. And then once you get that, it will show us the folder. So there's going to be a folder here onto your left tab. And it's going to show, once you mount your Google Drive, it's going to give you the folder of your Google Drive and Drive and My Drive. And then all your file will be in here, right? And to access the file, which is called avocado.csv, just go with, so I'm going to have a variable or path and going to get a string of, it's going to be the folder, which is folder drive, and then subfolder my drive, and then the file name, which is avocado.csv, right? And then if you want to look into the data, you first import the library first, which is the pandas library and the numpy library, which again, numpy is the library that do all the math application for you, and pandas is a library that handles the data modification, etc. for you. So this one I'm going to call data is equal to pandas.read CSV. So we're going to read that folder. I mean, read the avocado file in it, and then you run it. It's already mounted at the drive. So we're going to go in here and look at your data set. So this, I'm going to call it data, and you run it. And now the data, which is the panda data frame. Get that here. The data will read everything inside your CSV file, right? And then it will hold everything, and then you organizedly divide your data into like each data and all of the features and column, and it turns like, it basically turns from this this Excel or CSV file into something that we can work on it later. So this, I want to show you this. This is one way that you can import your data. There's also another way that you could do it, which is simply goes here, upload it. You click the upload, and then you drag the CSV file that you downloaded. But the thing is that if you disconnect it, the file will be deleted. So you have to do it every time that you disconnect to the Google Colab, right? So you come to here, you upload it, click here, upload it, and you bam, it will be right here, right? So then we change it. Instead of doing this, I'll just kind of comment everything. Instead of doing this, right, you can also do path is equal to just the file name, avocado CSV, and you do the same thing. So data, I would say 2 is equal to read CSV and then path, right? You run it, and then let it read the folder, read the file, and do everything. And if you run data 2, it will show the same table right here. So basically, there are 2 ways that you can import your file. Put it into the Google Drive, and then use this long version of a code, or you can simply just drag it in here and then write down the file name. But there's some cost and benefit within it. So like you can simply just run this section every time. But if you're gonna drag it every time that you log out, you have to keep dragging it every time. So yeah, that's something for you to know. So I'm just gonna keep it to data for now, so that it gives you the more consistent. So yeah. So after I have that, let me clean up this. If there's a way that you can look into the data instead of going data and have it return everything, which is gonna be like hundreds of lines of table. You can use the method called head, and it shows there how many rows that you want to have it shows instead of everything. So like head 5, it's gonna show you the first 5 data. And say if you have 8, it's gonna show you the first 8 data, and you can take a look at it too. And another way that you can do it is you can also call the data.info. This will return you all of the data and the type of the data. For example, we have the column name date, right? It's going to give you object, but in this case, it's just a string. And average price is like, it's going to be a float number, some similar to the table. So yeah, everything will be described in here. And it tells you how many entries or how many rows are there within this one. And once you get familiar with the data, you want to check if there's any null value, because let me think of some example. Let me just look at this. Yeah, sometimes let's say sometime that you want to do some survey, right? But then people don't answer some question. They just leave it blank. So that blank is going to be your null data, but that's going to be, so then you have to consider, okay, how can you consider that null data? Is there a way that you can like substitute the null data into something else? But that's like for the other time. But for this one, it shows you that there is no null value. So you can just simply run data.isNull.sum, and it's going to show you if there is any null value within each feature, which is none because they are 0. So everything is filled up. So that's great. And the next one is that you're trying to predict average price, so that put that into a separate data frame. So again, our data, we have an average price, right? So we want to only extract that particular column. So if you don't know it, the way I do it is just Google everything. Like give you some time to load my internet. Pandas, how to get only one column. Generally, there are lots of data into it, lots of examples. He simply goes into it and take a look at it. So this one doesn't say. So yeah, these ones say like using data frame and then bracket column name, and then it will return this. So okay, I'm gonna use that for my work. So we want to extract only the data average price, right? So we need to go data dot no bracket average price, and then you run it. It gonna returns all the column of average price. So like this 130, 135 is also come from here. 130, 135, etc., etc. Right? So we want to store that into the another variable so that it is easier for us to work on it. So I'm just gonna store it some in the y value, and then when you shows the y value, it's gonna show off this. And this one says stop unnecessary column. So for example, let me do this. Give me 1 sec. Yeah. So when you look into the column, you try to analyze the data. Okay, what are the columns that it's not necessary? This is unnamed column, and it's gonna have index of indices of index of each data. So that's probably not necessary. We can also simply drop it. The date is the string, and like we have to do all kind of calculation. But does it really contribute to the average price? Maybe we can just drop it, something like that. And so if you have all kinds of like, okay, all kinds of information, how can we do this? Again, just go with this pandas. How to drop column. So you look into it, it shows you some kind of example, hopefully. And you look into your example. So like this one, you already have, they say, okay, you have the panda data frame, and then you drop it by going with the bracket and then the column name, and then it will return this. So I'm gonna do that, do the same thing as well. So I'm gonna drop it and use, after I drop everything, I'm gonna store that into the X value. So that's gonna be out my feature. So then I can do the prediction from that feature so that hopefully I can get the average price. So this one is gonna be our data drop, and gonna be a list of column. So we already provide that, which is date, average, price, and name, and 0. So it should be list of that. Let me correct it quickly. And then once you show this text, you run it. Average price not in axis. Oh yeah. So now it shows not in axis. What does that mean? So let's look at this specific specification of this. Drop specific label from rows or column, but the default is 0, right? So axis default is 0. So we want to drop index. So now before it dropped the index, right? So basically it dropped the row rather than a column. So then one for column, one on column. So it's gonna change the axis to 1, and that will drop the axis, drop the column rather than drop the row. And you run it, and then bam, it will. You can look at the data. Now it doesn't have the data, the date, average price, and unnamed 0 column anymore, unlike the previous one. All right. So far, so good. Do you feel like you can rewatch it later, or I can also explain something else to you? I'll take silence as kind of okay. Again, yeah, you can ask me any question in the office hours, or email me or anything, or put it on Piazza. Yeah. So make sure that it's dropped. You can also just run start info to show all the features that are inside of here. Give it some time. All right. So it shows you, okay, there's X features that we want to include inside our features, and then do the linear regression. And now we're gonna introduce you a little bit of concept of one-hot encoding. So let me also change it to share my screen. Then give me 1 sec.
Can you go back to data drop real quick?
Yeah. This. Oops, sorry. Give me 1 sec. All right.
All right, thank you.
Yep. So there's a thing called one-hot encoding. So if you see from the lecture, or if you don't remember, that's okay. I can also talk about it too. So generally, right, the data doesn't even show you like the number. It also shows you like the string of here, right? You have some kind of string for each category. So you want to try to convert that into the number so that you can do all kinds of math operation to the number. And this is gonna comes into the concept of one-hot encoding. Right. So delay. All right, let's do this for now then. So then say for example, we have a data, we have a student ID, and you have 1, 2, 3, 4, 5, right? And you have that grade. Say student one is B, this one is B, this one is C, this one is A, and then C, right? Generally, yeah, you want to convert everything into the number. So you could say like, okay, let's change B to 2, B to 2, C to 3, A to 1, and C to 3. Yes, that also works, but it doesn't really. But if you look at the number instead of looking at the grade, if you purely look into it, you might see like, okay, so does that one might mean less than 2, or 1 is more than 2, or does 1 really have any other meaning rather than using 2? Or what about it if there's a number of 10? Does it like kind of like scale of each other, because 2 is like a 2 scale of 1, right? So then doesn't mean that B is greater than A by twice? Or if you flip it around, like if A is like 4 and C is like 2, does that mean like A is scale twice of C? So instead of that, we use the one-hot encoding, which I think we also discuss later, or we kind of discuss a little bit. So change everything to use everything, turn everything here inside this column into a feature by itself. So this one become A, B, C, right? So if the grade is B, you simply just assign it as 1, and everything else 0. Same thing with the second student, which is 1 and 0. The third student, assign 1 to C, right? And everything else is 0. And this one is A, student can, fourth student get an A, and this. And finally, you will get this, right? So now this data will make more sense that, okay, student A, student 4 get a grade of A. Student 1 and 2 get a grade of B, right? And you simply just drop this column. That's the main concept of one-hot encoding. And when you comes into the code, it's gonna be here. So give me 1 sec so that I make sure that I did not butcher every column. I mean every code. Yeah. So this one, you try to one-hot encode your category data. So basically, anything that is not their number, you want to do one-hot encoding of it. And if you run x.info, you see that there are 2 columns that shows that it's an object rather than an integer or a float, which is the type and region. So then you put put those column into a list. So this one category type, column type, and column region. You put that, assign that into the category data, and then this line, these two lines we provided to you, but basically the whole thing is that it will drop the, yes, this one drop the data from the X data and then convert it to the NumPy array, and then you do the one-hot encoding. Oh yeah, sorry, I should go back. But this one avocado category is only takes the data, the category data. So this LLC, the location is like a way to exclude data or include data, but that's like something for you to can also like look up beyond. But that's like the general term, like log includes data that are int or float, right? But this one, or this one, I should say, exclude or include data. But this one, in this case, we want to exclude everything else and keep the category data, which is the type, and region, which is string. But this one, avocado number, we say, okay, just drop these two so that we get the float instead. Drop category.
Wait, can I ask something?
Sure, go ahead.
Thank you. So all you're doing is just you're removing the categorical data from like the original thing and then making a new one with the like the ones and zeros that you showed.
Yes, because I have that. Yeah. We only yes. So we only want to get these data and then you turn it into one hot encoding. But if you like say have the height, right? And then you want height like some random number. I use centimeter. Sorry about that. But yeah, if you accidentally has the float number or some kind of number within here, right? Can you imagine what will happen if you also one hot encoding this one? You return every possible data. So like data range from like say 100 to 200, right? You're gonna turn it into the feature, and then you just put 0 and 1 into it. That's gonna create some kind of problem, and that's like something that you give it too many features, and then it's gonna make too much of the calculation for your computer. So that's something that we, instead of using that, we just exclude it out and let the number work by itself, but convert everything from as a string into the one hot encoding. Does that make sense?
Yeah, that makes a lot of sense because you're like making everything its own individual object that way.
Correct. Correct. Yeah, I like it. Yeah, you guys getting it so quick. So, all right, let's go back to here. So now you only have the categorical data, right? You use the one hot encoder method from here, or the object, which is one hot encoder, and then you fit the data. What do you want to fit to? So you only want to fit the categorical data, which is avocado dot underscore cat, right? And then this one asks, what are we transforming? So we want to get the avocado categorical. So this one, it does all of this work for us. Give me 1 sec. Yeah. If we do everything from converting this line dot encoder dot fit, it would do everything and then converts it into ones and zeros. And then this one encoder dot transform, so that we want to, I'm not exactly sure like the return type of the fit, but yeah, basically we have this object, right? We also convert it back to another object that to a type that pandas can work on it, because yeah, if you as a refresher, we have Panda data, we have Panda library to work on it, and Panda data frame, and now we do everything with the categorical. Do you want a hard encoding, and then you want to put back. So then we use this line, and you run it. So make sure your shapes make sense. So we want to check if the data is also as we expect. So we checking the shape of the array or matrix is a good way to do it. So you can simply print the one hot labels dot shape. That's going to give you the column of the one hot encoder column, and it's going to return I believe it's just array. Let me double check. Give it a sec. See, yeah, it's gonna keep all of the one hot encoder object, which is just a bunch of columns with ones and zeros. So this one shows the shape of the one hot labels, and then for we also want to check if the other things, which is the numerical data, is also has the same role, because we want to make sure that the amount of data sets remain the same, so that when we combine them back together, it doesn't create some error. So this is going to be the shape of the numerical, which has nine column, nine features, and this one is going to be your one hot encoder, which has 56 features. And the next part is that, yes, as I mentioned, we want to combine both of them together. So simply do this. So you can simply use the NumPy method, which is NumPy or np.concatenate, and this x is going to be equal to 1. So we want to combine these two together. So I just simply put them inside a list. So avocado, num, and one hot labels. And again, axis is that you want to combine both of them row by row instead of column by column, because we want to work on the features on the column instead of row, and then when we goes back into it, yeah, we just combine them side by side rather than the top and bottom. And then you run it, and you want to check your final. So let's check the shape first. See if prepare the shape. And it gives you this amount of shape, right? And you can also just look at it too. But the problem is that we convert it into not a pandas object, so it will show you some kind of list or arrays data. So then it might not be like a good way to look at it. But yeah, we can just kind of conclude from the shape that it does the task that we want. So then now you come into the train trace split, and as we mentioned, we want to get the training data and test data, and we want to build model based on top of the training data, right? So say if you don't know, like, how do you do it? So sklearn, how to split data, and you go to it. Okay, it shows you. Okay, you use something called train test split method, and you have all this definition, etc. And then you can also take a look at an example on how they do it. You use just split. You input the x value and then the y value into it, and then it returns you 4 things. And you kind of see of it, and okay, think of how do you also apply into your own data. And basically, this is honestly, this is also how it works. Like if you don't understand, Google it and then try to find, okay, what are the things that people do and how can I apply to my own project. So we want to, let's go with this. You can just copy from here so that you import the method, right? And I'm lazy, so I'm just gonna copy this and paste it here, right? No, I should copy the whole thing. This here. So which will it will take the x variable. So this one should be lower lowercase x because that's how I define it here. So just be careful with that. When you like copy everything, it doesn't mean that it will work everything with your variable. So I want to split the x data and y data, and test size is gonna be, the goal is that we want to split into 20%. So this one is gonna be 0.20%. Random state, we can ignore that for now, but in a short explanation, sometimes it will randomly split the data. So if you run it every time, it's gonna give you different data. So you want to assign random state so that every time that you run it, it will split the data consistently rather than randomly split the data into the test and train data. So that's how we do it, and we're gonna run it, and let's see how it goes. So let's check the shape. So x train dot shape and y train dot shape. Okay, so we can see that. Okay, now it's split correctly. It has the shape of the train. X train is have this amount, and which is the same of the Y train, and it has 11 feature. But this one is all, when it doesn't show, it just tells you that it has one feature, which is the average price that we want to predict, right? And these are 11 things, 11 shape that we would like. Wait, no, sorry. I forgot about the one hot encoding. It should be avocado prepared. Yeah, and you run it to split it again, and it gives you the shape of it, which is 65 column, like just as how we do it before. See, you can make some simple mistake. It's very easily. So you want to double check every data. And yeah, so now it does this job. So like from like 18,000, split up into like around 14,000. So that's good. That's the job for us. So now the next task is we want to get a linear regression and fit your model, and then get your prediction. And again, if you don't know, just go with this sklearn linear regression. Right? You get into it. You want to skim a little bit on the definition, and then maybe you're lazy. Yeah, just go for a copy and paste. So because you want to import the method, right? And you get the linear regression. And now you say, I want to build a model, and I just call it linreg. So which is a linear regression. And the way you do it is that as just like the earlier Python, the Jupyter notebook, the first one, we can just call linear regression dot fit, and you're gonna fit the train data and to fit the train data together. So like this one can be x test and y test, because we want to use the linear regression that we have, which is y is equal to x mx, y is equal to ax plus b, but this one can be obviously it's gonna have more columns. So then, but then we just let it do the job by itself. So you can call it linear fit and give it some time, and then it will does the job for you. And we want to say, okay, how does it do with the score, right? So then, no, with the test data. Sorry, So after we fitting and we let the model does all the calculation for you. You're gonna want to try to see how it goes. So this one check the shape of your prediction. So I'm gonna say predictions is equal to linrect dot predict, and it's gonna be x yeah, sorry, I messed it up with my spelling a little bit. This one you should fit the train data instead of test data. My bad. All right, and you do it again, and now you got the model, and then you try to predict with the test data, right? And then you can like print prediction, and it gives you a bunch of predict data, and you can try to like manipulate how you can print the x test and the prediction by yourself. But this one I'm just gonna show you how you can make a prediction with the new data. And this I would go with, I want to just simply check the shape of it, and that should hopefully be enough. So just prediction dot shape, and it gives you hopefully 3000. Yeah, and 3000 as this one. And the last module, and then we're done for today. All right, final push. So score your data using mean square error, which is the cost function that we just learned earlier. R square, R2, yeah, basically R square, and root mean square error. But root mean square error, I think, basically just take a square root of the mean square error, but we can just ignore it for now. And again, if you don't know, okay, how can I find the mean square error? Let's go for it. Scalar mean square error, right? And just look into it, copy that thing, take a look a little bit and how the example works, and just go say mean square error is equal to the method of mean square error, and I want to pass in the predictions, and that's the predictions from our base fit line, and while comparing with the true data, which is y test, right? And then print shows it up. It's gonna be mean square error. It's gonna be this. Let me see. So print it out and run it. It shows you that you have 0.07. That's basically the average distance between your prediction and your your observed data or your true value. But that also doesn't really tells you, kind of like I guess kind of like a meme, right? It's too much. Like, oh, depends on the context. If like that thing, yeah, a lot, but the other thing so little. So we also want to use another method, which is the R square. And I want to skip the whole Google part, so I'm just going to write down have it, which is scalar dot matrix, and you import R2 score, and R2 R square. It's going to be R square score prediction and y test, and print R square. It's going to be this R2, and then bam. So you can see that, okay, it's the R square for this model. R square gives you 0.17, which is kind of not really well in my opinion, but some people might say that should be good enough. That's for you to analyze the model and then decide for yourself if the model is good enough. And you might try to like change around the data, etc., to make the model predicts it better than you would expect. And phew, yeah, that's basically like the whole work of your worksheet. And again, I don't expect, if you don't understand everything, don't worry about it. Just try to like go through slowly go over to the recording and then go through everything slowly, and then try to understand like how I deal with some kind of problem in each step. And then hopefully you guys can also have some familiarity with how you can work with data and how you gonna handle any kind of problem. And yeah, that's pretty much it for today. Sorry, that's like today is so long. Yeah, I'm happy to take any questions, and I'm gonna turn this into office hours for around 20 minutes. Otherwise, if you guys don't have anything, yeah, I think I put that into the chat of the whole Google Cloud. Yeah, just work with it. And otherwise, you're dismissed. Thanks for coming, you guys, and thank you for sticking
Thank
with
you,
me for the
Nathan.
whole thing.
See you.
Bye. Thank you.
Yeah, no problem.
Thank you.
Uh,
Thank you.
Yes.
Thank you.